Good morning, all of you. So today's session we are going to discuss about the Unit 3, which deals with frequency response analysis. The last unit we discussed about time response analysis. So we know the importance of the time response. So what are the inputs and what will be the outputs? So any type of the response, the input, it will be in terms of its domain, and the time response we got it through time. That means in terms of time domain specifications. So especially in the second order time response, we analyzed there are different types of time specifications are there, starting from delay time, rise time, peak time, maximum overshoot, and settling time. So similarly here in this particular unit we are going to discuss about a frequency response analysis. Right, what exactly the frequency response? You might be knowing about frequency. So especially since you are from the electrical background, if I'm asking the frequency of our alternating current supply, that is AC supply, you may know that it is 50 hertz in India. Also in other places, especially some of the European countries and in US, you can say it is 60 hertz, right? So it differs. And how the waveform is, that also you know that the waveform is purely sinusoidal in nature, right? And why we call the AC wave a sine wave, that also I hope we discussed, right? Because it follows the rule of sine, right? The sine rule, it is the waveform is following. That's why we call it as a sine wave, right? So, in detail about this sinusoidal response, we are going to discuss in this particular unit, right? So I want to give you some of the derivations from what we are having in the generalized system. That is, in the second order system, we are having CFS by RFS is equal to omega n square divided by square plus 2 del omega n. Yes, that we already discussed in the time response. So the similar thing we are going to discuss in this unit is frequency response analysis, right? And the frequency response analysis, as I told, here it is like a sinusoidal input, right? And the transfer function here also, it will be in terms of sinusoidal, right? That is sinusoidal input to the sinusoidal output. So that we call it as the frequency response transfer functions, right? Therefore in the time domain transfer function, that is a different, right? Otherwise in the generalized transfer function is a different. So in the unit 1 we studied about the generalized transfer function. It is telling about Laplace transform of output to the Laplace transform of input. So once it is coming to the time, right, that is S domain, it is converted into time. And once it is coming to the frequency, that is the Laplace transform of the sinusoidal input to the sinusoidal output only, we can say. That is how we can get it. So that is the important thing here while we are studying the frequency response analysis. So the main thing here, what we are going to do means, listen, so wherever the S domains are there, that will be replaced by the sine term. So what actually we are doing means we are substituting, we are going to substitute S is equal to, that is S domain, S is equal to j omega. So this is the one important thing, that we need to convert this S domain to the sinusoidal domain, right? So wherever the term S is there, simply we can substitute j omega. That means it is converted into a sinusoidal domain, right? So here we are having the real term as well as the imaginary term. Therefore, the frequency response analysis, the main thing you need to know about the conversion, right? This domain, normally it is in the Laplace, that is S domain. Therefore, we need to convert the S domain into a Laplace domain as a sinusoidal domain, right? That is a very important thing in this frequency response analysis. So wherever we are going to start this frequency response analysis, the first thing is that we need to put we need to substitute instead of s as j omega. Why? Because since it is in the sinusoidal domain, right? So the frequency response analysis, as I told, everything is in the sinusoidal domain. We are keeping the sinusoidal domain as the reference for any type of the analysis. Therefore, what we have to put means we have to substitute s is equal to j omega. All right. So that is the important thing here. And always here we are having magnitude as well as phase angle, unlike time domain. So in the frequency domain we are having magnitude as well as phase angle. So why? Because we know that the sinusoidal waveform, just imagine, right, it is having their own frequency, right, and it is having the magnitude. The magnitude means that is how much distance, how much that is distance it is having in the graphical representation. You can see that. I'll show you one, for example, sinusoidal waveform. Just I'll try to draw. So here you can see that this is the sinusoidal waveform, means it is having some certain magnitude. Am I right? So here you can see that the magnitude is there. So we can call it as m of omega. And similarly, at which place it is coming for the zero crossing. So there will be some angle, right? Therefore, any sinusoidal function you will be having an angle also. That is angle, we call it as phi of omega. So these two things are important while we are going for the frequency response analysis, right? I hope you can understand. One is magnitude and another one is phase angle. The magnitude means that is how much it is having, how much supply it is flowing through that particular area, that particular system. Right, it is telling, it will tell about the magnitude. And the phase angle, right, it will tell about, that is how frequently it will come to the zero crossing. Depends on that only the frequency there, right? So both the things are responsible for the frequency response analysis, right? Both magnitude as well as this phase angle. So next thing is yeah, we are going to derive something in this frequency response analysis. I hope you can understand why, because you already studied the time domain analysis. So the similar version here we are going to do the frequency domain analysis, right? So for example, we call the transfer function. I am writing here like transfer function is generally written it as the generalized transfer function. I'm going to write the generalized transfer function. We can write t of s that is equal to c of s by r of s, right? So this thing, you know, that the generalized Laplace transform output to the Laplace transform of inputs, right? Now in terms of sinusoidal domain, right? So in sinusoidal domain, which implies what we have to put means we have to put s is equal to j omega. That is the important thing. Therefore, the transfer function is also t of j omega, that is equal to c of j omega divided by r of j omega. So wherever the s term is there, you can see that it was replaced by j omega. All right. And similarly, other thing also, if it is a feedback system is given or a open loop system, for open loop, open loop system, normally we call it as G of S, right? But now it will be replaced by G of J omega. And similarly, the closed loop system with the unity feedback is there, or a feedback H of S is there. We can write for closed loop system with feedback H of S, which implies we can write the closed loop system, that is C of S by R of S is equal to G of S divided by 1 plus G of S H of S. I hope this thing you know that since we studied all those things in unit 1, right? It is not new to you. Now, if it is a frequency domain, so everything will be replaced. That is T of j omega, that is equal to C of j omega divided by R of j omega, and here also it will be replaced by G of j omega divided by 1 plus G of j omega into H of j omega, right, like that. And now if you need magnitude as well as phase angle, how we can find it? So that is the important thing here, right? So if it is a open loop function, if it is a g of j omega, there means for example here the for this particular function I need magnitude m of omega, means we can write that's modulus of where it is, yeah, modulus of g of j omega, right? But while writing modulus, you should know that if it is the generalized thing I will write, I think you studied everything in mathematics, you might be knowing when I am writing, if it is a plus ib is given, right, is the term. For example, I need magnitude, means how I can write, means that is modulus of a plus ib, that is equal to root of a square plus b square. I hope you studied. Similarly, if you want phase angle, for the particular same thing I taken, that is a plus ib, that is equal to tan inverse of, that is imaginary part divided by real part. These things and all not new to you. Already you studied about while we are taking the magnitude, you have to take the modulus. While we are taking the phase angle, you have to take tan inverse of this thing, right? Therefore, every place you can apply the same. If it is a magnitude, if it is a phase angle, like that, right? So this thing also you should know while we are studying this frequency response, right, and the frequency domain specifications, like time domain specifications. The frequency domain specifications are also there, and here we are having a resonant peak, cutoff rate, resonant frequency, gain margin, phase margin, bandwidth, etc. So these things are there in frequency domain specification. Right? The time domain specification, you are having delay, rise, peak, overshoot, undershoot, settling, like that. And here it is not a single waveform, right? It is a waveform which is keep on crossing the zero, right? And it is sinusoidal in nature. Therefore, we are having a resonant peak, resonant frequency, cutoff frequency, gain margin, phase margin, etc. So those things are there in the frequency domain specifications. We are going to see one by one. Right. Before that, I will derive the frequency domain specifications from the second order so that it will be easy for you to understand. Let us take the second order system. The generalized second order system, we know that from the unit 2 we studied the C of s divided by R of s is given us omega n square divided by s square plus 2 del omega n s plus omega n square. Here omega n is the frequency, angular frequency, and delta is the damping ratio, right? So those things you studied, we are going to take that one. Let us find one by one or the frequency domain specifications of the second order system. So the frequency domain specification of the second order system, I'm going to find one by one, like the time domain specification. So here the important thing is the resonant peak. So we will find that one first. So for finding the resonant peak, what we are going to do means we need to consider the generalized form of second order equation. The generalized second order system, we know that. So I'm writing generalized generalized second order closed loop system. We can write it as C of s divided by R of s, that is equal to omega n square omega n plus omega n square. Yes. So now we need to convert it into a sinusoidal transfer function. So we are going to convert it into, so I'm writing convert into sinusoidal transfer function, which implies I can write it as C of, what we have to put, sinusoidal transfer function means substitute s equal to j omega. So while we are substituting s equal to j omega, here it becomes c of j omega divided by r of j omega, that is equal to omega n square divided by, instead of s square we have to put j omega the whole square plus 2 del omega n multiplied by j omega plus omega n square. So listen, simply I substituted s equal to j omega, right? That's all I did. Now what I'm doing means a small simplification I'm going to do. So that is equal to, so here that is equal to omega n square as it is. And one more thing, we know that j omega the whole square means omega square, and the j square it is minus, am I right? Therefore we can write it as minus omega n square plus j into 2 del omega n multiplied by omega, am I right? Just I taken j outside, plus omega n square. I hope you understood, right? Just expand j omega square, that is equal to minus omega square, that's all. Now what I am doing means I am going to take this omega n square outside. So how it will come, right? Before that we can split it into a real part and imaginary part also. You can make it into a simplified system, that is equal to yeah, here omega n square you can put it. Now what I am doing means I am taking that omega n square outside so that I can cancel each other. So the first term, I think I made a small mistake here. So here minus j omega whole square, so it will not become omega n, right? It is omega square only. Alright, now I am taking the omega n square outside. So the first term it will be minus omega square divided by omega n square, plus second term j into 2 del omega n, not omega n, omega, because omega n square we taken outside, so omega n divided by omega n square it will come. Therefore I can write omega divided by omega n, then plus here omega n square we taken outside, therefore omega n square divided by omega n square, so it will become 1. So I hope you understood. Just I taken omega n square outside. Listen, the first term minus omega square divided by omega n square, and the second term j 2 del omega I taken outside, then omega n divided by omega n square will be there, right? Therefore 1 divided by omega n will be there, am I right? 1 omega n and omega n will cancel. So here omega n square divided by omega n square, that is equal to 1. I hope you understood. Now what I am doing means just I am cancel this term and this term. Alright. Therefore the remaining term Remaining term we can write it and take the real part and imaginary part separate. So that is equal to 1 divided by, so the real part you can take this, that is 1 minus omega square divided by omega n square plus j into 2 del omega divided by omega n, right? So this is the final term, we will get it. So now what we are doing means a normalized frequency we are going to substitute. Now listen, there also we are having the damping ratio, no? So the damping ratio we are having the ratio of two different terms, and here also we taken it as a normalized frequency since it is a frequency domain specifications. So here the normalized frequency they named it as mu, and that is equal to omega divided by omega n. Right? Now we are going to substitute that. Right, it is only for representation, don't think that I am adding a new element, so it is not like that, it is only for representation and it is easy to represent. So we can write it as, if you are substituting this, it will be further simplified, right? That's all. That is equal to 1 divided by 1 minus this mu square plus j into 2 del mu. So I hope you understood. So here also we put the omega divided by omega n is equal to mu. That means this becomes mu square and this becomes mu, right? So that's all about the resonant frequency that we obtained, right? And it is given us m of j omega. So this is C of j omega divided by R of j omega. We are going to find m of j omega. I'll tell you. That is em of j omega. That means it will give us the magnitude, and similarly we are going to find the pi of j omega. That means it will give the phase angle, right? That two things are very important here. So as per our textbook here, it will be magnitude is given us. I am writing here magnitude magnitude em is equal to modulus of j omega. I given already, that is m is equal to modulus of j omega. Therefore here we can write it as m of j omega, that is equal to c of j omega divided by r of j omega. So this is the value, we got it. Now we are going to take the modulus for this, right? Therefore we need to take the modulus for this also. That is equal to, we know that the whole 1 minus mu square plus j into 2 del mu, and the whole thing will be in modulus. So modulus of 1 also we can put, anyway it will be in modulus. So modulus of 1, that is 1 square plus 0 square, right? That is equal to 1, you can write. So the numerator, that is 1 only. The denominator, that is 1 minus mu square plus this thing will be there. Therefore how it will be, this will become a root of 1 minus mu 1 minus mu square the whole square plus 2 del mu, right? 2 del mu the whole square. So here you can see that is we substitute that formula, that is a plus ib, the modulus if you are taking for a plus ib, that is a root of a square plus b square it will be, right? So the similar thing we substitute here also. So that's all about the resonant peak, right? The value, that is the root of 1 minus mu square the whole square plus 2 del mu the whole square. We can keep as it is, no issues. This is our magnitude, so I can write it as magnitude m is equal to, so always we need these two things. One is magnitude and another one is phase angle, and similarly the phase angle we are going to write phase angle, it is given as phi, which implies we know that tan inverse b by a, and here I can write phi of omega, that is equal to tan inverse of b here is 2 del mu divided by 1 minus mu square, right? So that this will be the phase angle, right? So any domain specification, any frequency domain specification, these two things we used to find, that is magnitude as well as phase angle. Well, listen, today's session we discussed about the resonance peak, right? So for the resonant peak, we taken the second order closed loop systems function, the function of second order transfer function of second order closed loop system we given us CFS by RF is equal to omega n square divided by s square plus 2 del omega ns plus omega n. So this thing we know that it is very generalized. Now what we are doing is just we are substituting s equal to j omega, since it is a frequency domain specifications, right? We substituted j omega here, therefore j omega the whole square, that is minus omega square. Right, now what we are doing means omega n square we taken outside, right, for a particular format we need it, right? Therefore in the numerator it will be cancel this omega n square, and the denominator omega n square it will be cancel each other. Therefore 1 divided by the time is like that. So here it is a real part and here it is the imaginary part. So if you want to find the real part and imaginary, if you are having the real part and imaginary part, and if you want to find the magnitude, it will be root of a square plus b square, right? If it is a is the real part and b is the imaginary part. The same thing here we applied. Listen here, modulus of j omega. So here it is m of j omega means the modulus we taken. So the modulus, it will give like modulus of 1 is equal to 1, and modulus of 1 minus mu square plus j into 2 del mu, that is equal to 1 minus mu square the whole square plus 2 del mu the whole square. So this is the magnitude, and similarly here you can see that the phase angle also, right? I hope you understood. Right. Similarly, we can find the other values also. The normalized, the resonance peak we find it. Similarly, we can find out the phase margin, gain margin, then cutoff frequency, etc. So all those things are possible. The frequency domain analysis, right? So up to this, if you are having any doubts, you can ask me. Otherwise, I'll move to the next topic.
No doubt, sir. Proceed.
The next thing is again some more frequency domain specifications are there, right? If time permits, we'll do all those things. Otherwise, we'll get the end results also. But the important thing in the frequency response analysis or to plot the frequency response, some graphical representation is very, very important in this particular unit, right? Therefore, how we are going to represent, that is, how we are going to plot this frequency response is the bigger question here. Right, so we need to do some analytical calculations. Then afterwards, the with the end results, we have to plot the graph. Right, the graphically in semi-log graph sheets or the ordinary graph sheets or the specially prepared Nyquist plot or by using embedded circles. So many things are there. Many representations are there to plot this frequency response. Right, but this particular unit we are going to see some of the frequency plots that is very important. That is how to plot the time domain. You can plot it in the normal graph sheet. There is no problem because with respect to rise time, with respect to delay time, easily you can plot it, right? If you are getting the values, and if you are getting the values very closer, the graph will be more accurate. So that will be the time domain specifications, right? But the frequency domain specification, it is not like that. Right, it needs a special appearance, right? Since it is having the magnitude, it is having certain bandwidth, it is having the phase margin, it is having the gain margin, it is having gain crossover frequencies, phase crossover frequencies, cutoff frequencies. So many things there, many things were included while we are drawing this frequency response plots. Right, for that, that is a very important thing. That is important plot, we call it as Bode plot. All right, even the MATLAB it is available. While doing the experiments in the control system, we can do that in the MATLAB. It will be much easier. But at the same time, right, we are going to solve it mathematically for the given system, and we are also manually going to plot this one Bode plot, right? Plot the frequency response, that is Bode plots. So this particular plot we are going to do it in the semi-log graph sheets, right? Some of you might be knowing and some of you may not know. That's not a problem, we are going to draw, but always you need a semi-log graph sheets, right, while you are coming to the coming sessions. Then only it will be useful for you. All right, similar graph sheet means it will be having many decades, right? That is 10 10 10 appearance, it will be there, right? It will be how we are plotting means, if you are starting from point 1, it will be point 1, point 2, point 3, point 4, point 5, point 6, point 7, point 8, point 9, then 1. Then after 1, it will not 1.1, right? After 1, it will become 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. After 10, it is not 11. After 10, it will be 20, 30, 40, 50. So such type of graphical representation, we call it as a semilog graph sheets, right? We call it as the semilog graphical representation. You are having the decades of columns are available in the semilog graph sheets. And there only we are going to plot this one Bode plot, that is one. And the second one is the polar plot, right? So it is having a circular appearance, right? And it is also having a magnitude as well as phase. So both the things are having the magnitude and the phase angle, right? If you are drawing a Bode plot, if you are drawing a polar plot, both the plots you are having magnitude and phase angle. So how to get the particular magnitude for that particular plot is the challenging thing, Right? If it is a Bode plot, the regulation and how we are arriving the result is different, and in the polar plot, the arriving result is different. And these two things are important in this unit. So once you are able to draw these two things, it will be okay for me in this unit 3, right? And other things are the M and N circles, an equals plot, and an equals chart. So all those things are the supporting things for the frequency response plots, right? So anyway, instead of deriving many subsequent equations or the subsequent this frequency domain specifications, I am thinking that directly we can go to draw this Bode plot, all right? So that will be very important. So any plot, always keep in mind, the first thing is convert it into sinusoidal domain. That means just substituting s equal to j omega. That is the first thing. And the next, magnitude means, always keep it in mind, you have to take modulus. Modulus means it will be, if it is a plus ib, then it will become, the output will be root of a square plus b square. And similarly, the phase angle means you need to know about the tan inverse b by a. So these two generalized specifications are very very important while we are calculating the magnitude and phase angles. So the rest of the things I will tell you the procedure how to draw. Anyway, on the coming class, coming session, we are going to draw the Bode plot, right? Then if you are able to draw the Bode plot, and then we will go for polar plot and other things also. So that's all from my end about today's session. And we will see the graphical representation of the frequency response in the coming session. Right. Thank you.
Thank you, sir.
Thank you.